with the solutions as I go to check my answers.
Mm-hmm.
When I got to the end of it, it ends up being you have 1 moment to solve for, and the components of the system.
Mm-hmm.
I got a negative answer for MR.
Oh, yeah.
Same magnitude, but your solution online, I believe.
I think somebody brought that up to me. I think, and I went through it. I think my answer is just negative. My answer is the one that's wrong on that.
Okay.
So the couple there. What was the answer?
For the couple.
Yeah.
Negative 72,000.
That was the one I gave, or that was the right one?
You gave 72,072.5.
Okay, and it should have been negative.
Yeah.
72,000 what? 7.5?
072.
Okay. So yeah, it should be negative. We just went through that in office hours with someone.
I had the same number.
Yes. I just, didn't move something to the other side or whatever. Algebra is hard.
Yeah.
All right. So coming up is exam 3. And what we're going to do for exam 3 this is Thursday, a week from today. So what's the date? The 3rd or something? 4th? 11/4. Oh! That's what I said at first. Second? Oh, yeah. Okay. 3rd. Anyways, next Thursday. If the 3rd comes and it's not a Thursday, that's not the right day. And the topics are going to be, so the new topics are going to be rigid body, statics, and centroids, and structures. And then it's also cumulative. The cumulative part isn't as big a deal in this class because everything just sort of keeps building on itself, but you should go back and look at those old questions too. Anybody have any questions about the test?
For the centroids ones, would we be given all those formulas?
Yes. Yeah, I'll give you a sheet that has, I'll give you a printout of the sheet that's on D2L. Yep.
Will we have the same thing for joints that we had in the last exam?
Yeah, I'll print that out too.
Okay.
All right. So now let's go back to structures. At the end of class last time, I gave a set of steps that work for every kind of structure. Structures in this class is the place where I make the biggest departure from the way that it's taught in textbooks and in other classes and stuff. So I want to justify that a little, and I want to explain the differences. So in most, or possibly all, statics textbooks, structures are broken up into 2 categories. The first is trusses. And the definition of a truss is that every member in a truss is a 2-force member. And I remember I mentioned 2-force members last time. If you have something that only has 2 forces on it, and it's in static equilibrium, then you know that those 2 forces have to be equal and opposite, and they have to be along the line between the 2 forces. They can be out away from each other or towards each other, but you can't have anything else. And so trusses are structures that are made up of members like that. Well, obviously that doesn't cover every kind of every kind of structure, because if you include the weight of a member, it's already not going to be a two-force member. And so they also use the category frames. And in frames, they're not two-force members. Well, they can be, but not necessarily. Not always. But you only have two members meeting at each joint. Okay. And that's been the way statics has been taught for many decades. Here's how we're going to do it. I don't break it up. So I don't break it into categories. One approach works for everything. And so let me talk about the benefits and the drawbacks of that. So the benefits of my way. The first one is that you don't have to, going into the problem, you don't have to think about categorizing the structure. And you don't need to remember different approaches. So you don't need to remember different approaches or categorize structures. If you just see a structure, you know how to go about it. And the second one is that the second benefit is that there are structures that aren't trusses or frames. That's probably the bigger benefit. So if you had a complicated truss and then decided you wanted to include the weight, so say you had a truss. Let me give an example. Say you had a truss like this, where all of these are pin joints. And you wanted to include the weight. Look at most of these joints. Look at this top one on the left. There are three members connected there, so it's not a frame. And if you look at this member on all the way on the left, that has a joint at the bottom, a joint at the top, and it has a weight. The weight is a third force. And so it doesn't fit into either of these categories. And so these two approaches that you usually see in statics books don't deal with these. Wouldn't let you calculate that. Okay, so those are the benefits of the way I'm going to do it. There's one drawback. And that is that for trusses, you can save a lot of time using the truss simplification. And And I guess the big reason that you save a lot of time is that you have a much smaller number of variables. And that's something that's worth considering, but, there was no internet, no good computer. Using computers for calculations was tricky. You had to get computer time or whatever. Like when these approaches were done, it was just a totally different world. You could Google truss calculator, and it'll take you to a bunch of websites where you can just enter in the locations of these joints, and it'll do the truss calculation. So if you have a truss and you want to do a calculation, you can use the approach that I'm telling you, or if you just need a quick answer fast, you can do it online. So I don't think of this as really that big of a drawback. Yep.
So I get, you're basically saying we're going to have one way to do it, and
Yeah.
maybe this is an irrelevant question.
Mm-hmm.
Because we're saying, it doesn't matter if it's a truss or a frame. But
Right.
in my mind, I can't, is a truss always like a triangle and a frame is always a square? Or
No, the frames can be all sorts of shapes. Trusses are usually, in 2D, trusses are usually, maybe always, made out of triangles. I think maybe you have to make them out of triangles, now that I think about it. And in 3D, they're made out of, what are the, tetrahedra? But, so I guess that's the easiest way to recognize what would commonly be used with the truss calculation. But again, if you decide the weight is significant enough to include it, those things don't work as trusses anyways.
So frames or anything else?
Frames don't allow you to have more than two members meeting at a joint. And so it's not everything else. The usual approach deals with two common things that you see, trusses and frames, but it leaves out a whole world of things that that you could see, So we're going to do one that works more generally. And yes.
Can you relate the truss to this thing we talked about in pin joint, like the truss? Those are the same or different?
The trusses are members connected by pin joints, where every member in the structure is just a two-force member.
Oh, okay. So they're always connected by a pin joint, right?
Yeah, they are always. In 2D, they're always connected by pin joints. In 3D, they're always connected by ball and socket joints.
Oh.
And it's funny, actually, like the things that you use truss calculations for, like bridges, they're not really connected by pin joints.
Oh,
But you make that assumption, and you get pretty good results by assuming that it is. Yep.
So just out of curiosity, you said it's related to stuff you do with, say, bridges.
Mm-hmm.
If you wanted to calculate how much that can support at a certain point, would you just keep altering a weight force at that point until you aren't in static equilibrium anymore?
No, this structure, so in this class, we're not ever dealing with like points where materials break, right?
Okay.
We don't ever make assumptions like this is steel and this is like it's. So the structures that we're going to deal with, that thing, no matter what forces you applied to it, mathematically would stay in static equilibrium. And so you can't do it until it fails. That kind of approach is the sort of stuff you start to get at in deform. But yeah, you're right about this. You would say, so if this was a bridge, there was a bridge going over the top, you would make the assumption that there's some known force pushing down here, some known force pushing down here.
Okay.
And then you'd use that to calculate these forces. And then once you had those reaction forces, then using the analysis from deform,
Okay.
like the next class, you'd say like that's going to buckle or that's going to be good,
Okay.
And at the end of going through a few, I'm just going to go through some structures examples. But at the end, I am going to talk about the truss simplification. We're just not going to spend any time doing problems, but I'll tell you what the idea is. Okay. Oh, one more thing I wanted to say. So for trusses, you can save, it reduces the number of variables a lot. And again, this approach is to me, this is just an outdated approach. You know, our calculators do all this stuff that people didn't have access to computers that did when people learned this way. So now we're going to do structures that give us systems of 15 equations, 21 equations. They have to be multiples of 3, by the way, because every member gives you 2 equations for Newton's second law and 1 for the rotational equation, if you're in 2 dimensions. Yeah, so we'll have problems where you come up with 21 equations. And then you'll just solve that using reduced row echelon form. It's, it takes a little time, but it's not that horrible. But you can imagine why that was not an appealing way to approach problems when you had to solve big systems of equations by substitution. All right. So let's say we have this. The structure is a 45, 45, 90 triangle. And all the connections are pin joints. And there's a force that's perpendicular to the diagonal member of 5,000 newtons. The lengths of both of these two members are 0.7071. So that means that the diagonal member is 1 meter long. And then there's a roller at the midpoint of the horizontal member to put it in static equilibrium. And we're going to neglect the weights. So I've been talking about all these times that you neglect the weights. Why would you do that? Well, yeah, that's the key thing. Like, yes, it does reduce the amount of work, but you can't always do it. The times that you can do it is just when you're applying external forces that are much, much bigger than the weight is going to be. And so if you did include the weight, it wouldn't change the answer very much. No matter how much you want to reduce the, simplify the problem, if the weight is going to add significant forces to the problem, you can't do it and get good results, So it really just has to do with whether the weights are swamped by the other forces or not. And we want to figure out the external loads on each member. Okay, so who remembers the first step? We're just going to go through the method, that structures method. That's not remembering, that's reading. They both start with R, but yeah, number. So we're just going to label each member. So we'll go 1, I'll do it like this, 1, 2, 3. If you chose a different numbering, things would look different all through the problem, and then at the end, the answer would be the same. And then just for reference, for talking about it, I'll number the joints A at the bottom, B, C. we're neglecting the weight, so is this a truss? Well, we have two members that are two force members. One has a force there and a force there. Did I say two or one? We have one. That's the only one that's a two-force member. This member 2 has a force there, and a force there. So that's no good. This one has a force there, and a force there. So you can't use the truss simplification here. This one you could use the frame simplification that books talk about, but
What will happen if you use the truss as one board?
yeah, you get wrong answers. Yep. Because the truss assumption is, the truss approach is based on assuming that all these members have is tension or compression. Remember, a two-force member only has equal and opposite forces pulling out or pushing in. And so you make that assumption. Well, if you made that assumption here, you'd be missing important forces. Okay, and now we're just going to go through one by one. I'll do a free body diagram of member 1. And I am also going to do something that I think is helpful if you get confused about what's happening at joints, because it can be confusing. Whenever you get confused, just take a minute and do this for yourself. Draw like a side view of the joint to figure out what's going on. So at the joint A, it's pretty simple. The only thing touching member 1 is member 2. So down here, there's a force on 1 by 2. Yes?
Are we saying that the pin joint at A and B are belonging to 1?
Yes. But it doesn't, it turns out at A it wouldn't matter. If either way, 1 is applying a force to 2 and 2 is applying a force to 1. But it does matter at the joint B. So let's think about that one. Well, let's think about all of them. So side views of the joints. Okay, so at A, we have member 1 and member 2 connected by a pin. This is the joint A. And yeah, just like you said, we're going to assume that that pin is, like when we isolate members, we're going to include the pin with the lowest numbered member. So we're going to assume that that pin is part of member 1. Okay, so now think, if we're isolating member 1, what bodies are touching member 1? The only thing is member 2. So all we have is that force that I drew, F12. And then when we isolate 2, what things are touching 2? Well, just member 1. It's really the pin, but it's part of member 1. Okay, so now let's go to joint B. So I'll think of that as like the bracket for the pin. That's the ground. And then we have member 1 and member 3. And there's a pin joint going through all of them. So I'll call this one G for ground. This is member 1 and this is member 3. So at this joint, the things that are touching it are the ground, member 1, and member 3. So what's the lowest numbered member at that joint? 1, and so the pin is part of member 1. Okay, so when we isolate member 1, what things are touching member 1? The ground? Well, I mean just at this joint B. So just the ground and member 3, right? They're each touching the pin, which is part of member 1. But what happens when we isolate 3? What's touching member 3? Just 1. Do you see that? Member 3 isn't touching the ground. The only thing touching each one of those is the pin, which is part of member 1. And so that's the stuff that can get confusing with this. And whenever you get confused, I would draw this side view out, and I think it can help clarify. So let's do it for joint C now. That's another pretty simple one. So we have member 2 and member 3 and a pin going through them. So which one is the pin associated with? 2. And so when you isolate member 2, what bodies is it touching at that joint? Just 3. And when you isolate 3, what bodies is it touching? Just 2. Yep, exactly. Okay, so now going back to the free body diagram of member 1, we've dealt with the joint A. Now we're up at the joint B. So looking at this side view, we can see that member 1 touches the ground and touches member 3. So there's a force vector here. I'll call it, I'll say there's a reaction at B. I'll just call that RB. That's the force coming from the ground. And then there's a force on 1 by 3. Any questions about that? Okay, well, now we're just going to do a rigid body analysis of this, of member 1, to come up with Newton's laws. We're going to get three Newton's laws, and those are going to add to our big system of equations that we're going to solve at the end. So rho, F, M, as an about point, let's choose this as the about point. And so for the force RB, what's the rho vector? 0. The components are RBX, RBY. Cross product says no moment. And now the next one, so this was RB. Now F13. What's the rho vector for F13? 0. The components are F13X, F13Y, and the moment is 0. And then the last one is F12. What's the rho vector for that? Yep, right. It's 0.7071 in the negative y direction from the about point. So that's 0, negative 0.7071. Anyone confused about that? And the force vector is F12x, F12y. And then the moment is 0 times F12y minus negative 0.7071 times F12x. So positive 0.7071 F12x. And so Newton's laws say RBX, RBY plus F13X, f13y plus f12x f12y is equal to zeros. And the moment equation says 0.7071 f12x is equal to 0. Okay, so I'm going to list out the three equations that we get from this. The first one says rbx plus f13x plus f12x is equal to 0. The second one says rby plus f13y plus f12y is equal to 0. And the third one says 0.7071 f12x is equal to 0. Okay, so three equations. We can check to see if we can solve for anything. So the variables we have are RB, F12, and F13. So how many variables is that? 6, 2 components for each one. So we have 3 equations, 6 variables. There's nothing we can do yet. We just have to hang on to these equations till later. Yep.
Couldn't you cut that down to 5 variables? Because equation 3 just basically says f12x equals 0.
Yes. And you can decide whether you want to do that. I tend to just, once you're writing out the matrix anyways, I tend to just keep everything, put it all in. So we'll have an equation that just says 0.7071 f12x is equal to 0, and you're exactly right. That.
Okay.
Yep. All right, any questions about the first body? Yes?
So you can use the about point as F1 to also.
Sure. Yep. I did it there because then 2 of the forces would have 0 moments instead of just one having 0 moment. But yeah, you can put it anywhere you want. Through this whole class, you can put it anywhere you want. So. All right, so now we're going on to body 2, the horizontal body. So at the joint A, if we look at this side view, the only thing touching member 2 is member 1. So we have a force on 2 by 1. And at some point, it doesn't matter where in this process you do it, but at some point you have to recognize the fact that we already have the variable f12, and so we don't want to introduce a new variable. We want to use Newton's third law to write this in terms of the old variable. So we're really going to write this force as negative f12. And then what kind of force is happening at the roller? That's acting perpendicular to the surface of rolling towards member 2. So that's an upward force. I'll just call that R. And then the last one is over at member C. So looking at this side view, what bodies are touching member 2? Just 3. So we have F23. On 2 by 3. I'm going to put the about point over here for this one. So the first force is F12, negative F12. What's the row vector for F12? Yep, zeros. The force vector is negative F12x, negative F12y, and the cross product is 0. The next force is R. What's the row vector for R? Yeah, half of the length, and that's, yep, in the positive x direction, so 0.3535, and then 0. And that force vector is 0r. So take the cross product, and you get positive 0.3535r. And then the last one is F23. What's the row vector? Yep, positive 0.7071, 0. The force vector is F23x, F23y, and so the cross product is 0.7071, F23y. So Newton's second law says negative F12x, negative F12y, plus 0r, plus F23x, F23y is equal to zeros. And the moment equation says 0.3535r plus 0.7071 F23y is equal to 0. All right, so these are equations 4, 5, and 6. So equation 4 says negative F12x plus F23x is equal to 0. Equation 5 says negative F12y plus r plus F23y is equal to 0. And equation 6 says 0.3535r plus 0.7071 F23y is equal to 0. All right, we have 6 equations now, so let's think about how many variables we have. We still have all the old ones. So that was RB, F12, and F13. Did we add any new variables? 2, 3, and the R, yep. So now the variables we have are 2, 4, 6, 8. This is just a scalar, so 9 variables. We can't do anything until we have as many equations as variables. So far it's been a little discouraging. It keeps running away from us. But so now what we're going to get with the last rigid body is that all the variables on member 3 are variables that have already come up. We'll have 9 equations and 9 variables in a system we can solve. Okay. Any questions about that rigid body? Okay, so now member 3. The diagonal one. Okay, so up at the top joint, let's think about the side view. So that's at the joint B. Looking at this side view of the joint, what members are touching 3? Just one, that's all. Okay, that's a mistake that you're very likely to make at some point, is thinking that 3 is touching the ground in this case. But if you look at the side view, are careful about which member the pin is a part of, you can avoid that mistake. Okay.
But
So
it's connected to 2, right? Like it should be touching 2 also.
yeah, but that's at a different joint. I'm just going joint by joint.
Oh,
You're right,
okay.
but we'll get to that one.
Okay.
Okay, so up at joint B, all we have is the force on 3 by 1. And is that what we want to call that variable? No, because we already have 1, 3. So I want to call that negative F13. And then at the midpoint, we have the 5,000 Newton force. And then down at the joint C, let's look at the side view of that. What members are touching 3? Just 2. And so down here we have the force on 3 by 2. Is that what we want to call that one? No, we already have 2, 3. And so now we have RB, F12, F13, F23, and R. So 9 variables. Oh, I'm getting ahead of myself. We haven't even done the equations yet. Okay, let's put this aside for now. Sorry about that. Okay, so row F moment. I guess I'll choose the about point down here. So for negative F23, what's the what's the moment arm? What's rho? Yeah, 0, 0. The force is negative F23x, negative F23y. Cross product is 0. And then for the 5,000 Newton force, what's the rho vector? Yep, good. So the 5,000 is negative 0.3535, positive 0.3535. And the force, that's at an angle of 225, if you wanted to do it as an angle, or you can think of it as just cosine and sine of 45 in the third quadrant. So 5,000 times negative 0.7071, negative 0.7071, which I think actually just comes out to negative 3535, negative 3535. That's times 5,000. That's the force. And then the cross product, well, if you notice, think about the way that, like you did moments more often in physics 1, you can see what this cross product is going to be. You have a moment arm of 0.5 with a perpendicular force causing a rotation that's counterclockwise. So this is going to be a positive moment of 0.5 times 5,000, so it's going to be 2,500. But that's dangerously close to like thinking about this stuff, which I just despise. So just enter that into your calculator like a little robot, and it'll give you that just as well. And then for negative f(1,3), what's the row vector for that? Yep. That's right. And the force is negative f(1,3)x, negative f(1,3)y. And so the cross product is positive 0.7071 f(1,3)y plus 0.7071 f(1,3)x. So Newton's second law says negative f(2,3)x, negative f(2,3)y plus negative 35,35, negative 35,35 plus negative f(1,3)x, negative f(1,3)y, with zeros. And the moment equation says 2,500 plus 0.7071 f(1,3)y plus 0.7071 f(1,3)x is equal to 0. So equation 7 says negative f(2,3)x minus f(1,3)x, bless you, is equal to positive 35,35. Equation 8 says negative f(2,3)y minus f(1,3)y is equal to 35,35. And then equation 9 says 0.7071 f(1,3)x plus 0.7071 f(1,3)y is equal to negative 2,500. Okay, so 9 equations, and then the variables, we have 9 of them. That's RB, f(1,2), f(1,3), f(2,3), and R. Okay, so let's just fill out this table once. Other times we can skip this, just everyone can do it on their own. But okay, so we need 10 columns, 9 rows. Okay, so the rows are equation 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we have 10 columns. Those are the variables. So variable 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And these are, I'll label these in the order we had them before. So this is RBX, RBY, F12X, F12Y, F13X, Yeah, 10 is the constant. F23x, F23y, r, and the constant. Okay, so for equation 1, RBX we have 1. F13x we have 1. And F12x we have 1. And those all add up to zeros. Everything I don't have numbers in is 0. And then equation 2, it's just the y components of all those same things. So RBY is 1, F13y is 1, F12y is 1. So this is 1, 1, 1. Everything else is zeros. And then the third one says F12x, the coefficient is 0.7071. Everything else is 0. And like you said, Ryan, it would be just as good to have used that at the time to say we know F12x is equal to 0, get it out of the equation. It reduces the system, but I tend to just put everything in like this. Okay, equation 4. F12x, we have -1. F23x, we have +1. And everything else is 0. Equation 5, F12y, we have -1. R, we have 1. And F23y, we have, where are we? 1. And then equation 6, R, we have 0.3535. F23y, we have 0.7071. Everything else is zeros. And then equation 7, F23x, we have -1. F13x, we have -1. And the constant is 3535. Equation 8, F23y, we have -1. F13y, we have -1. And the constant is 3535. And then equation 9, F13x, we have 0.7071. F13y, we have 0.7071. And the constant is -2500. Okay, so if you solve that, you get RB is 3, 5, 3, 5, negative 3, 5, 3, 5. F12 is 0, 3, 5, 3, 5. F13 is 0, nope. F13 is negative 3, 5, 3, 5, 0. F23 is 0, negative 3, 5, 3, 5. And R is 7071. Any questions about that? Yeah.
This one looks a lot like the one we did yesterday. Was it Tuesday?
Mm-hmm.
Where they're like all the same. What is? I don't have my notes.
Uh-huh.
What are we? What's the pattern we're seeing?
Okay, well, let's go through. We're going to take these vectors now, put them back into the free body diagram so we can see what the external loads are, and then the patterns will be more clear. Okay, so let's go back to free body diagram of member 1.
Actually, I have a question.
Yeah?
Test, what would be best to do for a question like this? 'Cause this is obviously
Takes a long time. Well, yeah.
Would we just be asked to make the equations, or?
Sometimes that's what I ask. Sometimes I give some values and have you do one of the members. And sometimes I give answers and ask you to translate those answers into the external loads on each member. I guess I would say you're right that that's an issue for making tests. We can't do much on a test if I do a problem this long. So, but I try to just break it up into pieces. Or we can do smaller problems like the ones where you have 2 members.
Okay.
I do that pretty often too, and that takes a lot less time.
Is it risky if you accidentally do a error, like one mistake affect the whole?
Yeah, I won't. A dumb mistake that doesn't look like it reflects an important misunderstanding or something, I don't take any points off for that. Because there's like you said, there's a million places where you can just have a negative wrong or this thing or that thing, yeah. Okay, so free body diagram of 1. Let's go back to our original one. This is RB and F13 at the top and F12 at the bottom. And so so I'm going to do it in 2 steps, I guess. So we have at the top 3, 5, 3, 5, negative 3, 5, 3, 5. Plus, we can just add these since they're at the same point. Negative 3, 5, 3, 5, 0. And then down at the bottom was F12. So that's 0, 3, 5, 3, 5. And so that says, if you add these vectors together, this just gives 0, negative 3, 5, 3, 5. 0, positive 3, 5, 3, 5. And that is a compressive force on each end of 3,535. Well, this member is the only two-force member, so we knew going into it, if you happen to spot that the forces have to be equal and opposite and along the line between them, and that's what we got once we went through all the calculations. And then a free body diagram of member 2. That looks like this. We have negative F12 on the left, F23 on the right, and then R in the middle. So negative F12 is 0, negative 3,535. On the right, F23 is 0, negative 3,535. And then the reaction from the roller in the middle is 7071. And so you have a downward force of 3535, a downward force on the other side of 3535, and an upward force in the middle of 7071. Those don't have to be along the line of the member because it has three forces acting on it. And so what's happening there is like it's like a combination of forces that's trying to bend that object, being pushed up there and bent down there. Any questions about that one? Yes? You should know how to do this stuff. On tests, I will ask you to show what the external loads are, but any one of these three would be okay with me. You don't have to show all three steps to get from here to here to here. You can do it however you want, but yeah, you do have to know how to get from the variable values that you solve for to external loads on each of the members. Okay. And then the last one, member 3. We have negative F13 here. So that's 3,535. Zero. And at the bottom we have negative F23. So that's 0, 3,535. And then we have the 5,000 Newton force. And so you have a horizontal force of 3,535, a vertical force of 3,535, and a force of 5,000 diagonal. Yep.
On the where 1 and 3 meet, wouldn't it be in the positive x direction?
Where 1 and 3 meet on so up at the top, we got a value for F13 of negative 3,535. But if you go back to that free body diagram of 3, this is negative F13 acting on member 3.
Yeah, let's go back to your free body diagram at the bottom.
Okay.
It's not in equilibrium the way you have it.
Oh, I drew it wrong. Yes, thank you. Thank you. Okay. Any other questions? I mean, this is, think of like feel the power of this, you know, like any kind of machine, any kind of combination of rigid bodies that's used to support loads. What you're always trying to do is you're trying to make sure that it's going to be strong enough to withstand it. And so what we have the ability to do now is look at this overall machine or structure or whatever, calculate what the loads are on the individual thing, and then you can imagine that knowing these loads is an important step for then figuring out, okay, if this is made out of steel and it has this thickness and whatever, what's the likelihood that this is going to break? That's the line of thinking that we start to get more into in deform. But the first step is to go from the overall structure with the overall loads and turn that into loads acting on each of the individual pieces.
In this example, we've got triangle, and then we've got our loads like right in the middle of two of the
Mm-hmm.
triangle pieces. It seems like that's like worst case scenario.
Yeah. It does seem like that's the case, yes.
Only if you start moving one of your members off.
Yeah, if you move one of the members.
Yeah, you're going to have, yeah. Well, actually, so after one of the next topics, maybe the next topic after we're done with structures, is we're going to start talking about internal loads. And we'll exactly be able to do the calculations that your intuition is telling you about. Like, you know, what are the internal, so basically we'll be calculating what the tension and the shear force and the bending moment are that one piece of the rigid body applies to the adjacent piece. And we'll use that to say, okay, this has a very high internal load. It's you'd use those internal loads then to calculate stresses and strains, and then you'd use the stresses and strains to tell you how likely this thing is to break. But yeah, you're right. There's something special about using the middle like that. Sometimes it's convenient, but it sort of maximizes the internal loads that thing has to withstand.
So then, my other question is, so if you have
That wasn't really a question. That was a statement. So really, this is your first question.
my first question,
That'll be the second statement.
Yeah, it could be a second statement. We'll see.
who knows? If you have one body and two forces, I'm trying to think of like, which scenario can I say that I will always have the case where you have the two forces going straight out along the line of the body?
Mhm.
It's only when you have two forces.
Yes, that's all.
Any kind of force, like it can be, or is it always? Because like I'm thinking.
Any kind of force. If there are only two forces acting on a body, and it's in static equilibrium, then there's no way that it can be anything but along the line. It could be in compression or tension, but remember, you might want to glance back at the picture I drew last time, the two pictures. If they're not equal and opposite, the thing will accelerate, so it's not static equilibrium. If they're not along the line between them, it'll rotate, angular acceleration, and so it can't be in static equilibrium.
So if we have like more loads, more bodies, you can get like more than 50 equation.
Oh yeah, for sure. You can get a lot. But there are companies where engineers are analyzing this kind of stuff, but there are zero companies where people are analyzing this stuff with hand calculations. So in a way, like what we're trying to do is understand this stuff carefully so that you can go and write programs that'll do it for.
Just remember, all this stuff that took us 30 minutes, a computer can do in like 2 seconds.
Yeah, exactly, right. Yeah, less. Right. Any other questions or statements?
Could you tell me in the next minute how much, like, what is there a relation between the that body where it has 3 loads on it and the other one that has 3 loads, the directions? Like, because this one is pointing out and the other one was pointing down. I feel like
No, I don't really have anything to say about that. There might. Yeah, I don't have anything smart to say about that.
I will just
Okay.
disregard.
Okay. Any other questions? All right, let's stop there. So I think what I'll do is I'll say the assignment is just all the rigid body problems, and I won't give another assignment for Tuesday. I know there's a ton, or not rigid bodies, the structures problems. So you can just start working through the structures problems as much as you can, and the test on Thursday is going to have structures in it. Okay.
And the homework's due Thursday.
I think, no, it's not. Is it? Isn't homework due today, or is that old homework?
This is the centroid.
That's the centroid.
That's centroid.
That's due today, right?
We've already
So structures homework won't be due for 2 weeks.
Okay.
Is there like problems or structure and centroid that we have to do?
Yeah, I think there are a couple of those on the problems.
Would that be more complicated?
You know, not really. You know, I mean, it makes it longer, but I mean, really, you're just doing whatever you're doing at that time. Yeah. So it really doesn't complicate anything.
Yeah.